So today we're happy to have Alexandre here, who told me not to try to pronounce his last name. But he recently got his PhD from Perimeter and is now at the KITP. And he's going to tell us about light ray operators and complex spins in CFD.
Yes.
So
thanks a lot for inviting me to speak here. So, indeed, I'll be telling you about some of our recent work on some aspects of complex spin physics in conformal field theory. So, let's start to motivate this work first. Now, in the past several years, we have learned many lessons in conformal field theory, especially in more than 2 dimensions, by thinking about the consistency of fundamental principles with the dynamics. And today I'd like to emphasize 2 of them. The first fact is that there exists a large number of so-called multi-twist operators in any CFT in more than 2 dimensions. And we'll soon discuss this fact in more detail to remind ourselves of what this means. And the second fact is that the CFT data must organize itself into analytic functions of spin. Now, these 2 facts follow from requiring the consistency of the dynamics in very Lorentzian regimes, namely in the light cone limit for the fact number 1 and in the Regge limit for fact number 2. They are, in a sense, manifestations of locality and causality, respectively. We would like to understand very well what constraints from Lorentzian physics imply on quantum field theories. And in particular, we would like to not have many confusions on these facts. So this talk is about reconciling some puzzles that arise when thinking about these 2 facts. But before I can tell you what these puzzles are, let me remind you exactly what these statements mean. So let's start with the first fact. Now, first I want to tell you exactly what multi-twist local operators are. And then I want to tell you what I mean by a large number. So the idea is that in any CFT, in the bigger than 2 dimensions, given some primary operators OI with some twists, which are defined by the difference between the dimension and the spin, there exist families of operators which accumulate in twists. You should think of these families as operators which are essentially composite operators made of some primary fields and some derivatives sprinkled in between. So for example, here we are considering triple twist families, which are families made out of 3 primaries and some derivatives. And this way of thinking about the operator in this semi-classical way is correct at large spin. So when S1 and S2 is large, claims that in this limit, the dimension of this composite operator asymptotes to the sum of the individual dimensions plus the spin. Holographically, you should think of these states as some particles or planets which are orbiting at large separations, much larger than radius of ADS. So their separations of order of log of the spin. And then locality will enforce that interaction die off, so that their energy is simply additive. By large number, I want to claim that the number of primary operators of this form grows fast with spin. So for example, in the case of the triple twist operators, if you try to count the number of operators of this form, semi-classically, you'll find that the number of primary operators grows linearly with spin. If you consider operators made out of n primaries, the number of primaries will grow as j to the n minus 1. Things clear so far? So now that we remember what multi-twist local operators are, I can already point out the first puzzle, which is the following. The counterpart of the statement that the number of operators grows with spin is that at small spin we have few operators. How can the CFT data be analytic in spin if you only see finitely many local operators at each spin? Namely, I have a huge number of operators at large spin. I continue down in spin. I only see finitely many operators, but I should have infinitely many trajectories coming down from large spin. So what happened to these trajectories that they suddenly don't contribute at some integer small spin? Do the trajectories just terminate as I'm continuing down in spin? that cannot be the case because that would be non-analytic. So what's the resolution? Before moving on, I need to describe more precisely what is fact number two. Now, Simon Caron-Roth, he used the Lorentzian inversion formula applied to a correlator, O1, O2, O3, or 4, to produce certain functions, C, which are labeled by the correlator, 1, 2, 3, 4, which are functions of delta and S that have the following properties. These functions have poles as a function of delta when S is an integer, at the positions delta I of all the operators that flow in the O1, O2, 2, O3, O4 OPE. Namely, you'll have single poles at delta I, at the position delta equal delta I, with residues that are related to the structure constants of the operator flowing and the external operators. This is valid at integer spin. Moreover, this function is analytic in spin. What this means is that by tracking down the singularities of C when we continue in spin, this will define analytic continuations of the CFT data. Namely, if we track the single poles, the position of the single poles as we continue in spin defines the continuation of the dimension in spin. If we track the residues, that will define the continuation of the structure constants. There's an issue with this construction, which is puzzle number 2. For me to make this puzzle clear, let me first mention that because local operators appear in every OP up to global symmetries, this function C constructed from different 4-point correlators will have poles at the same location delta I at the integer S. Namely, if there's a local operator, if it appears in different 4-point functions, all of the C's built from these different 4-point functions will have a pole at the same location corresponding to that local operator. We call this local operator universality. Local operators are universal in the sense that the same operator appear in different 4-point functions. The question is whether the singularities of C delta S at non-integer spin also satisfy this property. Namely, are the allocations of single poles away from integer spin the same, no matter which external correlator I consider, or each correlator sees different analytic continuations of the CFT data?
Which part of that is the puzzle? Do you want them to be the same?
The puzzle is whether there is universality of whatever flows at continuous spin. A more advanced comment is that there's an interpretation of these singularities in terms of some non-local operators called light ray operators. A different way of phrasing this question is whether light ray operators are also universal, in the sense that the same light ray operators control the physics of different correlators. Now, I want to emphasize that these puzzles really arise because of higher twist trajectories. It's somewhat easy to reconcile these two facts in the case of double twist trajectories. Indeed, let's consider some weakly coupled conformal field theory, in which we can make this very explicit. So let's consider some free field phi, and let's consider this non-local operator O2, which is built by integrating two fields along a light ray at positions alpha 1 and alpha 2 against some kernel. Here I should normal order this operator, I forgot to add. Okay. What does this formula gives us? The first comment is that this operator is manifestly analytic in spin. The spin dependence only enters through this kernel, and the kernel is analytic in spin. So the operator is analytic in spin. Moreover, near S, near an even integer, something simplifies. Namely, this kernel becomes non-integrable when S approaches an integer, even integer. This divergence from the integral is cancelled by a pole of the gamma function. And more precisely, this kernel as a distribution has a finite limit to the 2kf derivative of the delta function. Which means that as S becomes close to an even integer, this non-local operator reduces to the null integral of a local operator, which is precisely the double twist operator. This means that If we now consider matrix elements of O2 with different states or operators, they provide manifest continuations in spin of the matrix elements of the double twist. The matrix elements of the double twist correspond to CFT data of integer spin. And then for the matrix elements of O2, they find continuations in spin of double twist trajectory. Moreover, in the sense of puzzle 2, it shows that these continuations exist on their own right, in the sense that it doesn't matter to which correlator O2 contributes. The matrix elements are well defined. One way to understand why the double twist trajectories are simple is to recognize that O2 is fixed by kinematics. Indeed, our goal is to continue this integral, null integral of the double twist operator. And you can check, it's an explicit exercise to show that this operator transforms as a primary inserted at null infinity with dimension 1 minus 2k and is even under CPT symmetry. It's free fields, you can just act with conformal generators on that object and check that this statement is true. Requiring that O2 preserves these properties, namely that it's also CPT even and transform as a conformal primary of dimension 1 minus s, imposes that the kernel is even, translation invariant, and homogeneous of degree minus 1 minus s. The kernel I wrote there is a unique distribution of these properties, so it's fixed by kinematics. So far, we discussed the free theory. Perturbatively non-interaction does not affect this discussion because we simply multiplicatively renormalize this operator and modify the homogeneity through an anomalous dimension. So everything remains true in perturbation theory. When you consider higher twist trajectories, things are not so simple. The main reason is because their numbers grow in spin, and we'll see how that complicates things now. Let us try to repeat this exercise and construct perturbative twist-free light rays. Let's consider this ansatz, where we now integrate three fields in three-field theory along the light ray against some kernel. Requiring that O3 transform as a primary, we will then enforce translation invariance of the kernel and homogeneity of some given degree. However, this is bad news. Suppose you construct such a kernel, we can always multiply it by any function f of the cross ratio, alpha 1 minus alpha 2 over alpha 2 minus alpha 3. This cross ratio is scale invariant. It's also translation invariant. And therefore, multiplying this kernel by any function f of this form will still lead to solution to this constraint. This leads to a naive continuum of triple twist trajectories, which is not what we expect. Reggie theory indicates we should have discrete trajectories, and we find a continuous of them. So the question becomes, what quantizes this continuum of discrete trajectories? So the goal of this talk is to try to answer these questions very explicitly by examining twist-free single trace operators in planar and equal spring mills at weak coupling. We'll then try to extract some more universal lessons out of this explicit computation. So the first thing we'll do is to explicitly construct the twist-free light ray operators and understand from this explicit computation what conditions quantize this naive continuum of light rays. Then we'll relate the matrix element of these operators to the continuation of the CFT data, which will allow us to understand why we only see finitely many trajectories at integer spin. We will learn, moreover, that these infinitely many trajectories, they unify at complex spin, and they form a unique Riemann surface as we continue in spin. Namely, you can move from any trajectory to any given other trajectory by performing analytic continuations. Crucially, we'll show that this happens in perturbation theory. So in the literature, people have noticed sometimes at finite coupling in any source spring mills that you can move between trajectories. Here we are going to show that this happens in perturbation theory in the multi-twist sector. Namely, at one loop, you can already see the full Riemann surface. And the last thing I'll point out is that despite what I'm telling you, that this organization of the spectrum that's provided by light ray operators is not unique. And in fact, there are infinitely many other ways of organizing the spectrum into distinct Riemann surfaces, which would represent optics. Okay. Any questions so far? Okay. So let's get our hands dirty and move on to n equals 4. So we'll consider primary operators of the following form. They're single trace operators made of 3 complex scalar fields Z and S derivatives along some null direction, plus permutations of these derivatives amongst the various Z fields. At fixed S, there are many operators of this form that are primaries. We will label all of them by an index n. At free level, all operators of this form are degenerate. They all have dimension 3 plus S. At one loop, these operators, this degeneracy will lift. And here I plot the one loop anomalous dimension of all operators of this form as a function of S for operators of even spin. It's very easy to generate large tables of data like this. I showed all operators up to spin 150. I could have extended this plot up to spin, say, 3000. That would not be too hard. And the reason why it's easy to generate these plots is because the dynamics in this theory is integrable, and therefore there are very good tools to compute this type of on-shell data.
So is gamma, the anomalous dimension, is it normalized by some sort of small coupling constant? So is there some scale on the y-axis?
Yeah, so this is the one loop anomalous dimension. So the dimension is delta plus g squared times that gamma. I took out the g squared.
Given it's one loop, why don't you have an analytic formula?
There's no analytic formula
Because
for this anomalous dimension. There is an analytic formula for the lowest, for the leading twist in the sector. It's given by 8 harmonic number of S over 2. For the higher ones, it does not. And this is consistent with what I'm going to show you. I'm going to show you that all of these points, they belong to an infinitely shitted Riemann surface. So there's no hope of having some exact formula for this, even at one loop. The main feature I want to emphasize is that their number grow in spin as we discussed. So at spin 0, there's a single scalar, is the BPS operator. At spin 20, there are 4. At spin 100, there are, I don't know, many. What we want to do first is to build light ray operators which continue these operators in spin. So we'll proceed like in the introduction. We'll more precisely want to continue their null integrals as we did for the double two lists. So we want to continue these objects away from integer spin. And we will start from an ansatz, which is just the integral of 3 insertions along a trace in a light ray against some kernel, which will now depend, will be an analytic function in spin, but will be different for each trajectory. So n will index trajectory. We require that the light ray transform as a primary with dimension 1 minus s and spin minus 2 minus s inserted at the minus null infinity. And we also require the operator to be even under CPT. And the reason we do so is because it can be shown that at integer spin, these properties are true, and we want to continue the operator while preserving these properties. Now, these kinematic constraints translate into requirements on the wave function. Namely, they require that the wave function is translation invariant, homogeneous, reflection symmetric, and cyclic symmetric. These first 2 conditions are the statement that the light ray is a primary. This third condition is the statement that it's a singlet under parity and time reversal. And the last condition is the statement that it's a single trace state. It's important to trivialize kinematics before we start thinking about dynamics. To do so, we'll introduce 2 variables, r and theta. They are defined so that alpha 1 minus alpha 2 is r cosine theta, alpha 2 minus alpha 3 is r cosine theta minus 2 pi over 3. The last condition follows from trigonometric identities. And then, in terms of these variables, translation invariance is just a statement that we can write the wave function just in terms of r and theta, the center of mass alpha 1 plus alpha 2 plus alpha 3 drops out. Homogeneity becomes homogeneity in R. reflection symmetry means pi periodicity in theta, and cyclic symmetry means 2 pi over 3 periodicity in theta. They combine to pi over 3 periodicity in theta. We are left with the task of determining this function g of theta for each trajectory n as a function of s. Presumably, these are a set of discrete trajectories. Determining this function g is a dynamical question. Presumably, we could try to constrain g by requiring that it diagonalizes the one-loop dilation operator. However, this dilation operator is quite annoying explicitly. It's some integral operator that acts on the light ray, and it's hard to work with explicitly. Instead, we'll take a shortcut. We use the fact that dynamics in this planar theory is integrable, which means that the local operator in this theory, they diagonalize infinitely many so-called higher integrable charges. And here, we'll simply conjecture that this remains true for light ray non-local operators. So that non-local light rays simultaneously also diagonalize these higher integrable charges. Now, these higher charges can be constructed very explicitly at one loop, and they are somewhat simple. So I'll now describe how to construct these charge operators. The building block is the so-called R matrix. It's a very simple object whose is a matrix whose elements are essentially the generators of the conformal group. So for example, the first element is U, which is a parameter on which the matrix depends on, plus the dilation operator acting on the point of field insertion. Here we have the momentum generator, special conformal, and so on. Now, once you build this R matrix, you can construct this transfer matrix operator, which is one parameter family of operators labeled by U, which is defined by its action on the light ray operators in the following way. We have 3 R matrix, each of which is acting on one of the insertions of the light ray, and they are concatenated as a matrices along a trace. This defines the transfer matrix. Now, this transfer matrix is useful because of this property. The first is that it commutes for different values of the spectral parameter U. And the second is that it commutes with the dilatation operator. So it's consistent to simultaneously diagonalize the dilatation operator and the transfer matrix. So we require the light rays do that so that T of U is the eigenvalue, which encodes all these integrable quantum numbers of the light ray. In our case of triple twist operators, tau of U is a cubic polynomial because each R matrix is a linear function of U, which means that this equation, in principle, imposes 4 independent differential equations on the light ray, because cubic polynomial has 4 powers of U, a constant one. However, 3 of these 4 independent equations are trivializable or ansatz. In other words, they impose that the light ray is translation invariant and homogeneous. One of the equations is always trivial. We are left with one non-trivial equation, which takes the form of a third-order ordinary differential equation on G, which depends on S as well as Q, which is one of these integrable charges associated to the trajectory N at spin S. You should think of this equation as some kind of one-dimensional Schrodinger equation for G, where Q plays the role of energy, essentially. Q is defined as the constant part of the transfer matrix eigenvalue. So we are to solve now for G and Q simultaneously. Now, if you look at this equation, it's a periodic function of the coefficients are periodic in theta, which suggests us to go to Fourier space. So let's introduce the Fourier decomposition of G, where we expand into frequencies which are multiples of 6 because we have pi over 3 periodicity from the discrete symmetries. We introduce this factor of -1 to the n for convenience. And once we plug this decomposition into the differential equation, we learn that it reduces to a beautiful 3 terms recursion relation, which can be analyzed quite explicitly. Therefore, we have reduced the problem of quantizing and constructing the light ray operators to the much simpler problem of quantizing this Q and understanding the boundary conditions for this recursion relation. Now, we can push the analogy to the Schrodinger equation further, and claim that it's natural to assume that the quantization conditions for this problem are associated to analyticity properties of G. It's much the same way like usually with analyticity of the wave function in quantum mechanics to quantize the spectrum. Now, analyticity in theta is related to asymptotics in Fourier space. So we are led to examine the asymptotics of the Fourier coefficients an for large n. And we do so, and then by analyzing the recursion relation at large absolute value of n, we find the most general possible asymptotic solution for the recursion relation, which says that the recursion relation must have at most two terms asymptotically, one which decays as n to the -1 plus power 1 over n corrections, and the other which grows as n to the s plus 1 over n corrections. Recall that usually faster decay Fourier space translates into smoothness properties in position space. So if we aim to look for the most smooth solution, we should look for the solution for which there is no growing piece in Fourier space. So we look for the solutions. We look for solutions for which alpha 2 is 0 as n goes to infinity, plus infinity. Once we fix the boundary condition at plus infinity through this requirement, we can then reconstruct the solution using the recursion relation. So we start at plus infinity, we apply the recursion relation systematically to lower n, and in this way you reconstruct an for all n. We can do this numerically, for example. So we apply the recursion relation many times to lower n from plus infinity, where we control the function through the asymptotics, and this gives the solution as a function of q and s. Notice that the asymptotics you get at minus infinity is independent, right? You fix at plus infinity, use the recursion relation to lower it, and then at minus infinity, you might get a combination which is decaying or growing. So it's a non-trivial connection problem to determine the asymptotics at minus infinity, given the asymptotics at plus infinity. So let us plot for fixed s, what's the ratio of the growing part divided by the decaying part at minus infinity as we fix alpha 2 equal to 0. Is the result as a function of q. So you see that there are discrete values of q for which it's possible that alpha 2 is 0. So log of alpha 2 from goes to minus infinity means alpha 2 is 0. So at these quantized values of q, there are solutions which have pure 1 over n asymptotics, both at plus infinity and minus infinity. The claim is that this corresponds to the first light ray of the first set of operators, the second light ray, the third light ray, and so on. So the claim is that this provides a solution of puzzle 3. That the naive continuous applied ray operator is quantized by demanding analyticity properties of the wave functions as, for example, the field insertions in the light ray collide control values. Indeed, having constructed the light rays, we can now verify or claim and check by, for example, acting with the dilation operator and plotting the anomalous dimension analytically in spin. And this is the result. So the light ray dimensions are given by the dashed lines. They beautifully interpolate all the local operators, and they do so in the most obvious way possible. If you gave the points to a kid and asked for them to connect the points, they'll probably draw these curves. So you see that there is a first trajectory, second trajectory, third trajectory, and so on. So the light ray analyticity tells you how to assign operators into families. And given this assignment, they define a unique continuation which does not grow exponentially in the right half plane, in the sense of Coulson's theorem. So it seems that we have succeeded in constructing the light rays. So now we can try to explore what physics they tell us. Now, as I said, in the right half plane, things are as simple as you could imagine, just these basic trajectories that never intersect. However, the claim is that as you continue to the left half plane, you find branch points. So here's a schematic picture of what happens. In the right half plane, there is nothing. In the left half plane, you find infinitely many branch points, which are given by these stars. These branch points are located in finite positions in the spin plane, so they do not disappear as the coupling goes to 0. And as you perform monodromies around these branch points, you continue one operator family to the next. So for example, if you start from the second family on the right half plane, and you go around this branch point, and you go back to the right half plane, you end up in the third trajectory. And this happens at one loop. The same happens, for example, between families 2 and 4 in that branch point, 3 and 5 there, or 3 and 4 there, and so on. There are infinitely many. This gray region is just a region where we don't have very good control of the analytic continuation numerically. And so we find some branch points, but the claim is that there might be more here, and we are not confident. But outside the gray region, we claim that we found all the branch points, and this picture continues to the left, and there are more.
Wait, can you go back, like one slide to the?
Oops.
Shouldn't, I thought there's like also this shadow transform, so shouldn't you have like the reflection of this plot to the left-hand side anyways?
So that's the first place. So we're considering a trajectory which perturbatively has fixed twists, so it's a diagonal trajectory like this. Has infinite degeneracy. There are many trajectories here, which are this. Then it's true, this plot has shadow symmetry, so there's another set of operators that live here. Moreover, in gauge theory, there are so-called horizontal trajectories, it's called BFKL trajectories, which are like this. So this is S, this delta. Yeah. And yes, it's true, there's this trajectory, but this mixing here happens non-perturbatively. Okay, so here we're discussing things in perturbation theory. So we're saying that in the complex plane, there are other branch points beside those which lift and correspond to this. In other words, it's true, there will be mixing between these two trajectories, and they will correspond to poles in the left half plane. So for example, some of these poles correspond to mixing of the diagonal trajectory we are considering with the shadow. Here we're saying that there are also branch cuts which correspond to mixing of diagonal trajectories in itself.
Can you say more about the this mixing, if which family can be converted to which family?
Yeah, so
Is it every single one? And
yeah, so it's every single one except the first one. So the first one is the one that, as you pointed out, we know analytically a lot about it. Anomalous dimension at one loop is a harmonic number of S over 2. The way you can think about is that that family has additional symmetry. It's parity invariant. And because of this symmetry, it doesn't mix with the others. The others are generic, and therefore they're all allowed to mix.
So it's not a property of supersymmetry that this thing, like
That they mix.
it's not related to the fact that in the first trajectory the BPS guy sits. That doesn't.
That is related to the fact that that trajectory is special.
Protected.
It's not protected, only the one operator is protected, but it implies that, I mean, for there to be the BPS state, it must have this parity symmetry at least. So yeah, being very direct, all trajectories except the lowest one, they mix. Of course, even operators and odd operators, they are in separate sectors as well. So all operators mix with odd operators, even operators mix with even operators, but otherwise they all mix.
and the pattern mixing. I mean, here
It
you showed some
seems-
simple things.
It
but
seems to be that they are all square roots type. They all have a radicality 2 in the branch points.
And it's a one family becomes another family and there's nothing more complicated or?
Yeah, that's what I think is implied by having radicality. So, it would be very interesting if something more exotic could happen as you start moving in the coupling, where these branch points could collide or something like that. But that's beyond what we can do. It's also possible that it's in this gray region where we don't have good control, something more exotic is happening. That's why we really can't do it. But from the region where we have good control, all we observe are this type of square root control similarities.
So what's the problem where you're losing control? But is it when you apply this recursion relation in N?
Let me explain how we did. So let me give the slide and that will apply. So here's an actual picture of the monodromy, not some schematics. I'm plotting the complex S plane, and here I'm plotting this, the real part actually of this integrable charge Q. I could plot any other observable associated with the operator. And to generate this, so this corresponds to two sheets on the right half plane, the second and third family of operators. And as I perform this monodromy, I go from one operator family to the next. To generate this plot, we need to solve the quantization problem numerically for 10 to the 6 points in this plane. And the way you do it is essentially through some kind of Newton method. And what happens is that when you go close to the negative real axis, the roots for this problem that you're trying to solve, they get very close, and so the numerics get very unstable. So it's hard to distinguish roots, because there are many operators that are coming together there. Because I suppose the physical reason is that they all need to mix with the VFAL trajectories. So they all need to coalesce there. So here in this plot, you can, if you have very good eyes, you can see some discontinuity here. And that's because there are two more branch points there that connect with another sheet that's not being plotted. Okay, so now let's go back to the right half plane. And let's discuss puzzle 1 again. So here, at say spin equal to 20, there are infinitely many trajectories, but we only see 4 local operators. How can that be? One possible solution is to say that, except for the first 4 trajectories, in which there are local operators, and in which the light ray reduces to the null integral of a local operator, we have that for all the other infinitely many trajectories, the light ray operator has 0 matrix element with any states. In this way, these higher trajectories will then decouple from any local correlation function.
Is that for a trivial reason or is that something?
That's a dynamical statement.
So by any state, you mean a state that's generated by a local operator? Yes.
All states are generated by local operators in the form of theory. It's a dynamical statement. Whether there is, for example, symmetry reason of seeing that CFTs have this dynamical property is something that we do not know. I'll comment further. But as I'll show, well, I'll not show, but as I'll mention, you can convert this statement into some rules for the standard CFT data of local operators. Let's move on.
Oh, sorry, by dynamical, you mean it's highly non-trivial, that you don't have a simple argument?
Well, that's correct. One argument, though, is that this is required for consistency of the existence of multi-trace trajectories with an Artesian spin. So in a sense, it's a constraint on the CFT data that's imposed by causality and locality. However, we need to be a bit more precise before claiming that this is a resolution, because this statement is not really a physical statement, because it explicitly depends on the norm of the light ray. In other words, it could be that this matrix element is going to 0 just because the norm of the operator is vanishing, and not because of the dynamics. A more refined statement is to say that the analytic continuation of the structural constants of the local operators, which is something that's physical and norm independent, and is for the in the trajectory that's defined by the light ray vanishes at small integer spin. So to check this, we need to understand better how the matrix elements of the light ray define these continuations of structure constants. And the answer is that they're given by a formula which is manifestly independent of the norm of the light ray, which is given here. So I'll explain this formula now. So this formula determines the structure constants continued in S in terms of two dynamical correlators in CFT. This 3-point correlator of the light ray and two local operators divided by a norm of the light ray. The other three factors are simply kinematical factors. For example, this bottom factor here is just the standard 3-point structure with appropriate quantum numbers for this 3-point correlator, which cancels the position dependence of the dynamical object, so that this term in parentheses is really just a number and not a function of positions. This is now just a number, and that function there is just a number that you need to be careful with some factors of 4 pi and some trivial functions of S.
What is this O bar?
Well, it's just
There's something supposed to, yeah, light ray operator acting on the vacuum. Because that's
so
it's not light ray operators.
we'll get there. So this is just, again, this is just a shorthand notation for some 2-point structure with correct quantum numbers to cancel this. Now, what's the definition of this object? We'll get to. As you're pointing out, defining a norm for the light ray is non-trivial. This was also noted by these authors in a similar investigation. And the reason it's non-trivial is because, well, one would naively define the norm through this Whiteman correlator of two light rays. But this is 0. The reason this is 0 is because a light ray operator acting on the vacuum is 0. And so this is 0. The reason, on the other hand, that this is 0 is the following. Suppose it were not 0, then this is a transformed as a conformal primary acting on the vacuum. So this becomes a primary state with continuous spin. And there are no states that transform as primaries of continuous spin in unitary CFT. Therefore, this must be 0. So this cannot be a good definition of the norm. Let us thus consider a different possibility, is to consider the time order correlator of two light rays. New problem. Now this is infinite. Why is this infinite? So recall that each light ray operator is given by integrating over the position of 3 fields. So if you want to compute this correlator, you would have one light ray, another light ray, you do weak contractions, and you would integrate. However, in these integrals, there's one particular subintegral which corresponds to integrating over an orbit of a non-compact conformal transformation that preserves the integrand. So there's a symmetry that preserves the light rays, and one of these integrals is integrating over the orbit of this conformal transformation. Because it's a symmetry, the integrand is invariant, and you have a 0 mode. It's non-compact, so the integral of the 0 mode is divergent. However, now we know how to fix it, because since it's a symmetry, we can just gauge fix it. So this gauge fixed time order correlator is what we'll define as the norm of the light ray. And indeed, once you define this object, one can show this continuation of the structure constant is given by the formula in the previous slide. When the dust settles, all we need to compute this continuation is to compute carefully these two dynamical correlators with weak contractions, which, once you perform the computation, you can reduce the 3-point correlator to a single integral over the wave function we fixed with the recursion relation times some kernel, which is known, it's just determined by the weak contractions. And here, for the norm, it's just a double integral over 2g's and a kernel. You can perform these integrals numerically, for example, for each trajectory at each spin. Okay, so now I can finally tell you what's the result. So here is the integer spin, local CFT data for the structure constants. I plot their logarithm as a function of spin. This is the analytic continuation as determined by light rays. So what do we see? We see that for the integers, integer spin below where we have local operators, the structure constant goes to 0, meaning the log goes to minus infinity. So the structure constant indeed vanishes and the trajectories decouple. And so this resolves puzzle 1. But also recall puzzle 2. We now have a definition of the structure constants that's intrinsic in the sense that it doesn't make reference to which 4-point function the light ray contributes to. So it suggests light ray universality. Let's summarize this puzzle and this resolution. So we started with two statements, one that follows from locality, one that follows from causality. There are multitude trajectories that accumulate in spin, and they form discrete trajectories, which are analytic. We're claiming that to reconcile in any conformal field theory, there must exist infinitely many detectors or light ray operators ON. You can think of them as detectors, which for integer spin have 0 expectation value for any state. Meaning you can create a state by inserting a local operator, and then you let this state evolve in time. You make a measurement at full Chernow infinity with the insertion of the light ray, and this must be 0 for any state. We check this in a computation in planar n equals 4. This group checked the same is true in Wilson-Fisher in the epsilon expansion. And because of the reasons above, we expect it to be general, because it's the only way we can think how to reconcile these two facts. In fact, I want to tell you that this is a constraint on the dynamics. Namely, with some mild extra assumptions, you can show that this implies some rules on the CFT data, where these extra assumptions are the statement there is no level crossing for these trajectories in the right half plane. This is true in any source perennials, for example. It has already been used as a bootstrap constraint by Julius and Nikita Sokolova to fix the 3-point functions of gravitons and subleading massive string trajectories in the 1/8 RADS expansion in the ES5 process 5. So I want to move on to the last topic I want to discuss today in the last few minutes. Now, the light ray operator construction we discussed in this talk provides a way of organizing the spectrum into analytic trajectories. It does not show that this organization is unique. So in the last few minutes, I want to explore the following question. Are there alternative ways of organizing the spectrum into analytic trajectories? How could we approach this problem? Suppose I give you the dimension of a sequence of operators starting at some spin S0, and then I tell you what's the next dimension in 2 units of spin, 4 units of spin, and so on. How can you tell me if this sequence of numbers admits an extension into an analytic function with good Regge behavior? Well, there's a beautiful theorem, which I'll quote some simplified version, which is the following. Suppose that this sequence indeed admits an analytic extension in the right half, and is analytic in the right half plane and sub-exponential, meaning in the right half plane, it does not grow exponentially. Then the claim is that this function admits a convergent representation as a series, which converges in the right half plane, which determines the function anywhere in the half plane, analytically in S, entirely in terms of its values at the integer spin. Now, given the sequence I told you, you can just test. You just take this formula, you plug the sequence on the right-hand side, and you check numerically where this expression is converging. If it's converging, you claim that indeed this is a good trajectory. If it diverges terribly, you claim, no, that was a bad assignment of numbers. So let's try this method. Let's take the standard sequences given by light ray operators, plug in the equation, and we find beautiful convergence. You can reproduce the dashed curve for all these black trajectories by plugging them just the local operator data onto that formula. On the other hand, if you try to plug the sequence defined by this red curve, so the black dots that are along this red curve, you find terrible divergence in that formula, which means that we do not believe the red trajectory is actually an analytic trajectory, which is something that everyone probably would say is obvious because no one would say that this red curve is analytic. Indeed, now you try to do many different assignments and you find terrible divergence unless you choose these very carefully tuned lightly operated trajectories. Only that, not really. We find infinitely many other trajectories beyond those of light rays which converge. So here's the same plot as before, except that I'm dividing the anomalous dimension by log s to make it easier to visualize. And I'm introducing these red dots, which are the operators with odd spin that I had not plotted before. In this plot, the light ray trajectories would be like this line here. These trajectories are new. They have an important feature, which they interpolate this physical spectrum in steps of 3 in spin, not 2. So they go from spin 6 to 9, 12, 15. They mix even and odd spin operators, and they are analytic trajectories which behave appropriately in the right-half plane sub-exponentially. I told you how to learn about these trajectories numerically, but indeed there's an analytic argument, and this dashed curve is actually an analytic curve, which make us confident that our claim is correct. These are new analytic trajectories in the system. And this is not it. Indeed, there are trajectories which organize the spectrum in steps of 6, 9, 12, any multiple of 3. So here is steps of 12, for example. Now, the existence of the standard trajectories follows from good Reg physics, as Simon Caron-Roth told us, by considering the Reg limit of 4-point correlators and requiring that it's consistent. These new trajectories, on the other hand, who ordered them? Why do they exist? Is this due to some causality constraint in high boost limits of higher point functions? Is this an artifact of integrability or large n? And it's very special to planar dynamics in N+4? Or is this something more general that is a new universal property of CFTs, which we have not noticed before? We do not know the answer to this question. We do not have good arguments for or against any of this. So if you have, you should let me know.
So can you investigate these questions in the Wilson-Fisher?
That's a very good example. So I do not have the data of Wilson-Fisher at hand. If some person that has this notebook could give me, I could immediately apply this game and check. I should email Peter, that's true. So once I email Peter, I can do some, okay, let me just make one comment. If I just plotted this figure without the blue lines, you kind of can see that the blue lines are very regular, right? You would not be surprised if I claimed it as analytic. If you look at the spectrum from Wilson-Fisher, you also see some curves that are very regular and would suggest that there's something more going on than what you would naively say. So if I had to bet money right now, I would say that this remains true in the Wilson-Fisher. It's less regular than N=4 though. So it might be more settled there. Anyway, even if it only holds in planar N=4, it's an extremely powerful constraint. As I said, analyticity in spin can be converted into sum rules on the spectrum. This is telling us that there are infinitely many more sum rules than previously realized that should hold in N=4 at least in the most twist sector. And this should be used when attempting to bootstrap these correlators in this theory. So there's clearly still a lot of things to be learned from Lorentzian physics in CFT. So thank you.
But these new trajectories, do they correspond to some new, like, definition, like new objects in CFTs? Like, lightweight operators you can form like
Is
you
there,
can do the
is
lightweight
there an
OPE
operator?
and you can study many things.
Is there an operator interpretation of
Yeah.
this trajectories?
Yeah.
The answer is we don't know. As I said, there's an analytic argument for defining these curves. The same is true for the steps of 12, although I don't plot here.
Yeah.
This analytic computation is a very integrability-based computation, and it gives an interpretation in terms of quote unquote, with very big quotes, the worksheets of n equals 1. What that translates in space-time is in 4D is hard to guess from there. So short answer is there seems to be some type of operator definition from n equals 4 that's still to be understood, although we have some hints. But no, we do not have a good understanding yet. These trajectories cannot exist due to miracles. So let's say that this claim is true, that there is something, at least in n equals 4, that happens in higher point correlators that forces this analysis to undo. This computation will then suggest what type of operators are dominating. To understand what kinematics require the existence of these trajectories, these kinematics will suggest which type of operators, non-local operators, should dominate that region of the dynamic. And that will tell us what to do. But at this point, I don't know what to do.
Is there a statement where, like, if you have some number of alternate trajectories, then there must be an infinite family? Could it be finite in some other theory?
It could be finite. Again, there's no argument for anything, so let me point out, which is that going back to these zeros of the standard trajectories, which is, it could be that there's a more direct way of understanding this, or some kind of selection rule. But we do not have such an argument. I know there are a lot of people in this building that think about symmetries in non-local operators. So it's a question for you.
Thank you.